Okay, welcome everyone. Thank you very much for coming to this, the first lecture on a course called Information Theory, Pattern Recognition and Neural Networks. This first lecture is an introduction to information theory. Information theory was invented by Claude Shannon to solve communication problems. And the fundamental problem that Shannon defined was the task of reliable communication over an unreliable channel. So that's our fundamental problem. And I'll give some examples right now. So, some examples of channels. One channel we're using right now is the channel that goes from my voice to your ear, and the medium is air. Another channel that we may be using is a channel that goes from our eyes up to other bits of our nervous system. And there the medium is sort of bags of cytoplasm and electrical impulses. Another example of a channel that we're all carrying around with us is DNA. We've got about 10 to the 13 copies of our genome on board us in each of our 10 to the 13 cells. And every time one of those cells replicates, we send 2 copies of the genome into those cells. Repeat that 40 times and you've gone from an egg to a human being and maybe on to the next generation. And another example is the spacecraft, say the Mars rover or something like that. You'll have an antenna on Earth and you use the vacuum as your transmission medium and send signals to the Mars rover, and maybe it's got an antenna and sends back signals. So this is a channel that can go in both directions. And another example is a phone line. So you maybe have a copper wire, if you're old-fashioned, connecting one phone to another phone. Another example is a disk drive. So the medium is some sort of magnetized film in a standard hard drive. And in that disk drive, you store a message, which might be your file, and you send it to yourself at another time. So many of these channels go from one place to another place, one place to another place, but you can have channels that go from one place, the disk drive, to the same place, but at a later time, and we're still trying to communicate a message from that one location to another location. And all of these channels have in common the property that the received signal isn't identical to the transmitted signal. So because of noise or other processes, our received signal is maybe approximately equal to the transmitted signal, but we've got some noise added as well. Maybe some of these channels, maybe there's no relationship, no simple equality relationship at all. You just have the transmitted, the received signal depending on the transmitted signal in some way. But for a toy channel, we might say, let's assume the received signal differs by adding some sort of noise. And in most of these applications, we might say that's bad news because we would really like reliable communication. We would like to be able to deduce at the receiver precisely what the original transmitted signal was. So we would like to have communication systems where the received message, is equal to the original transmitted message. That would make for a better phone call, a better disk drive, a better communication between lecturer and audience. So imagine that we're trying to achieve this goal. We're trying to make a reliable communication system. What sort of approaches could we go for? What solutions are there? Well, we can perhaps categorize solutions to this goal in two ways. Either they're physical solutions, where you throw away the lousy disk drive and replace it by a better one that's more expensive. That maybe you take your copper wires and you put better insulation on them. You use a colder magnetic film, you add cooling. So you change the physics to reduce the noise. So there's physical solutions. Alternatively, we could talk about system solutions. And the idea of a system solution is we accept the lousy channel as it is, and we add encoding and decoding systems around that channel to turn it into a reliable channel. So this is a much more exciting approach than the physical approach. Physics is exciting too, but the system approach accepts the unreliable system as it is and transforms it into a reliable system. And that's what information theory is about. We're going to be taking source messages, and our source message, which we might call S, is going to be put through an encoder system, an encoder which we will design. And that encoder will spit out the transmission, T, and this coded transmission then gets sent over the channel. The channel will do its thing. It will add noise, perhaps. And then we'll get a received message, R, which is going to be a corrupted version of this coded message. But then we're going to have another system. And the system is going to be called a decoder. And we will invent that too. And the decoder will try and come up with a guess for what S was. S with a hat on top. Hat meaning guess. What's going on here? The encoder is going to be some sort of system that adds redundancy. And we'll think about that in more detail in a moment. And then the decoder makes use of this known system for adding redundancy to try to infer both T and N, or if you like, both the source message and N. So the decoder is going to be a system for inferring N and S. Okay, let's give ourselves a toy model to think about. The toy model that we'll work with for a while is called the binary symmetric channel. So the binary symmetric channel has got an input, and we'll idealize and assume that that input is a 0 or a 1. So it's a binary input. You get to choose each time you use the channel, is it a 0 or a 1 that you send? And then what comes out is also either a 0 or a 1. And we're going to assume that the probability that what comes out is what you put in is 1 minus f, which might be 90%, say. And the probability that it is not what you put in is f, for example, 10%. So whenever you put in a 0, there's a 10% chance a 1 will come out, and there's a 90% chance a 0 will come out. And symmetrically, the other way around, if you put in a 1, there's a 90% chance you get a 1 out, etc. So that's the binary symmetric channel. There's probably very few channels in the real world that are the binary symmetric channel, but it's a nice simple model to discuss that has all the essential properties that we need to study this bit of information theory. So we could think of this as a model for a disk drive. Let's say you've made your new startup company, you've got Cambridge Blue disk drives, and you make your first prototype disk drive using your new invented technology, and you test it, and you find it flips 10% of the bits. Is that a useful disk drive? Well, let's just have a quick think. Let me ask you question number 1 here. Question 1. Oh, goodness me. Let's try again. Okay. Question 1. A file of 10,000 bits is stored on this disk drive. It's stored on a disk drive that flips 10% of the bits. And then it's read. Assuming that f is 0.1, assuming that each bit is independently either flipped or not flipped, roughly how many bits are flipped? Whoops, how many bits are flipped? And I'd like you to discuss this with your neighbour and give the answer in the form roughly this many, plus or minus this many. Does everyone understand the question? Okay, please talk to your neighbour, and then we'll see what numbers go in here. Number of flipped bits. Anyone?
1,000.
1,000 plus or minus? How many?
We're still debating.
Debating, okay. Anyone else say 1,000 plus or minus? Plus or minus 100? Plus or minus 900? $30? Okay, we've got a few answers there. Who wants to give a reason for their answer? So anyone who gave an answer, give a reason? $900 sounds quite a lot, doesn't it? Who said 900? Yeah, why plus or minus 900?
I had a quick look at
The data book, excellent, good. Because you don't need to understand things if you've got the data book. And what did the data book say? Okay, and you're looking at the variance of what? Binomial distribution. Grand. Yep. Very good. So you look up the binomial distribution, and it's got a mean of n times p, where p here is f. And it's got a variance of npq, where q is the other thing. It's 1 minus f. All right, so you can look that up, and then you need to know what variance means, how that relates to, well, roughly plus or minus, 1,000 plus or minus what. So this is the mean. It's 10,000 times 0.1, which is 1,000. The variance is 900. But what does that mean? What's the meaning of the variance? It's the square of the standard deviation. Okay, so this is the square of the standard deviation. You take the square root of it, which is 30, and that tells you roughly how many bits either way you'll be flipped. Okay? Now, the binomial distribution is pretty much the only bit of mathematics you need to know for this course, and I do encourage you to review the binomial distribution and get good at working with it, because we are going to use it over and over in this topic and in other topics in information theory as well. Okay, so we have an answer of 1,000 plus or minus 30, thanks to Mr. Binomial, the inventor of the distribution that bears his name. Okay, so we've got our disk drive. We launched the company, and are we going to have a happy customer when we sell the first disk drive? Any opinions? No? Why? It's slightly too many flips, isn't it? If someone's storing important information. So, question 2. To have a saleable disk drive, saleable 1 gigabyte disk drive, if it were a disk drive that's a binary symmetric channel, how small would its f have to be for you to be able to make a successful business? How small does the flip probability f need to be? Please turn to your neighbour and have a chat about this question. Okay. Any answers? How small do you need your f to be to have a saleable disk drive, to have a viable company? Yes?
10 to the minus 13.
10 to the minus 13. Any other answers? 10 to the minus 5.
This drive needs to be more than a gigabyte nowadays.
That's true. Many people need 20 gigabyte disk drives. These lecture notes are about 3 years old. So, yes. We'll put a little star here to say, please pretend that you are set in the past 3 years ago. We can redo it for another size of disk drive, but let's stick with gigabyte for the moment. People still use gigabyte USB sticks, don't they? Okay, so trying to make a saleable USB stick. Some other answers? Don't be shy. Yes? 10 to the minus 3. Wow. Any other answers? We've got quite a range of answers there. Yeah. 10 to the minus 10. Okay, so let's have some explanations from the extremes of the range. So that's these two teams. So where did 10 to the minus 13 come from? What was your...
So this was assuming there was no kind of protection. That would give you roughly about every 1,000 times you fill up the hard drive, you would expect to have a bit flip.
Mm-hmm.
So that's when you get to unsigned variable tape.
Okay, every 1,000 times you fill the drive. And your judgment was 1,000 was enough. Okay. Right. So where did 10 to the minus 3 come from? Okay, so let's just redo this calculation. Let's kick the tires on it a little bit. So let's imagine that our customer is going to use the drive every single day. They're going to be a fairly intensive user. And let's say that they might use the drive for 5 years because they're stingy and they believe in sustainable use of resources. So let's say you've got 5 years of use and we're going at a rate of 1 gigabyte per day. Then the number of bits that will be sent through this channel is 5 years times 1 gigabyte per day, and 1 gigabyte is 8 times 10 to the 9 bits, and 5 years is 5 times 365 days. So that's our number of bits that we want to send. And if you multiply that out, you get 10 to the 13. So that's very much on the same page as this sort of number. But do we want to sell it and say, yeah, we're expecting a failure within 5 years? Maybe that's not quite good enough. We'd like it to be quite unlikely that our first customer will ever complain. Yeah? So if we want a 1% chance of disappointment, disappointment being that any file at all gets messed up, then we need the error probability to be something like 10 to the minus 15. And if you want your first 1,000 customers all to be happy, then you need to aim for 10 to the minus 18. Okay? A 1,000 happy customers pushes you towards wanting 10 to the minus 18. And if you talk to the disk drive industry and you say, what is your industry standard for performance of a disk drive? The answer is 10 to the minus 18. So that's what they're aiming for. For today, let's accept 10 to the minus 15 as a reasonable answer. So we're aiming for an error probability of 10 to the minus 15 or better. And we now want to step back to the diagram I just rubbed off that talks about encoders and decoders. I'd like to discuss ways of adding redundancy. I'll clean the board, and if you can have a chat to each other about how could an encoder work? How could we add redundancy to a file? Okay. Now, I'm not asking you to give me an encoder that solves this problem straight off. I'm just asking, what are some encoders that add redundancy at all? Okay? So do we have some ideas for how to add redundancy? Yeah. Parity coding. What does parity coding mean, Gus? Okay. So we're taking some string of zeros and ones that we want to transmit. Like this. How long is the string that we're going to do the parity of? A byte. So maybe take 8 of them. 8 bits. Oh, that was 8. That was lucky. And then that's what the source came up with. And then we add an extra parity bit here, who we'll call P. And he's the sum of those. 1, 2, 3, 4, 5. So we write in 5 here, except we're using binary, so we write 1, because 1 is the same as 5. Okay? If it had been 4, we would have written 0. So that's a parity coding. That's a way of adding redundancy. Good. Any other ideas for how to add redundancy? Repeat things multiple times. So we'll have what we call a repetition code. How many times, for example, would you want to repeat? Twice? Okay, so we'll call repetition codes R, and I'll write out the code. we're going to take each bit, and as we send it, we'll repeat it some number of times. So we could send 0 and then repeat it twice, which I'm going to, from now on, call repeating 3 times, okay? That's repeated 3 times, and 1 gets sent as 111. And we'll call this R3. And I accept you could call this repeating it twice, because you send it, then you repeat it twice, but I'm going to call it repeating it 3 times, okay? That's my convention. And I made one of those earlier, and this is what it looks like. So we've got a file of 10,000 bits on the left, and then we repeat it 3 times. I've actually reordered the bits, so the first bit is sent after the whole file has been sent. So we repeat the whole file 3 times. But that's logically just the same as repeating each bit. So let's give ourselves a source file. And the source file could be the string 01101. And we transmit 000 111 111 000 111. Okay, so that's how we encode a file. And let's now give ourselves some noise and start talking about decoders. And we'll start with the repetition code. So let's have a noise vector. And the way I'll represent noise is it's going to be 0 if no flip occurs, and there's going to be a 1 if a flip occurs. So here's a noise vector that our binary symmetric channel could produce for us. And that would then mean that the received vector differs from t in some of these places. So 0, 0, 0. This one was flipped, so we get a 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1. So that's our received vector. So what did I do there? I added the transmission to the noise, and I did the addition modulo 2. So 1 and 1 is 0. Okay, how should we decode this? A decoder is a system that reads in a received file and spits out a guess for S. So, in general, how should we decode R3? Have a chat to your neighbour. Okay, any suggestions of how in general? Yes, at the back. Okay, so take the mean of each group of 3. Is that what you mean? So we read it 3 at a time, and you say, is the mean above, closer to 1 or to 0? Okay? Did anyone else have another way of putting the same concept? Yeah? Best of 3, or majority vote. Yes? So we reckon that the sensible decoder is the best of n, here 3, n's the length of this block that we're transmitting. Best of 3 decoder, or majority vote decoder. All right, so if we receive 0, 0, 0, we say 0. If we receive 0, 0, 1, we say 1. If we receive 1, 1, 0, we say, whoops, we say 1. If we receive 1, 1, 1, we say 1, 1. Do chip in if I make errors. Okay, so there's 8 possible received vectors, and here's what we do according to this decoder. And if we apply that decoder here, then our S hat comes out as 0, 1, 1, 1, 1. And what we can notice in this case is that some good things have happened. So here, a flip occurred. That was a flip, and it's being cleaned up because this is the same as this, and so that makes us happy. And something else has happened. Here there were 2 flips in a block, and this has been turned into a 1, and that's actually an error. So that's not good. So we're a bit sad about that. But fair enough, maybe this decoder does improve things. So if we apply the majority vote decoder, this is what we get. And if you compare the fluffiness of the source file and the decoded file there, you can see it's improved things. We have reduced the probability of error. So this repetition code kind of works a bit, but it doesn't actually get us to 10 to the minus 15 probability of error. Now, before we proceed and say, how do we make better encoders and decoders, I just want to prove this intuition. Why is the majority vote decoder the right decoder? So, as I said earlier, decoding is inference. We want to infer what the source message was. And to do inference, we need to use inverse probability. And I just want to remind you how inverse probability works, because in due course we're going to do slightly more complicated problems where you may not leap to the correct answer quite so easily. So inverse probability needs the rules of probability. The rules of probability are the product rule, which says that the probability of two random variables, for example, the source bit and the received vector, can be written as the probability of S times the probability of R given S. And it can also be written the other way as P of R times P of S given R. So that's the probability rule. That's just the definition of conditional probabilities, if you like. It tells you how to get a joint probability from a marginal probability and a conditional probability. Then the other rule of probability, and there are only two, is a sum rule. And the sum rule tells you how to get a marginal probability by adding up all values of a joint probability. So you can sum over all values of S, P of S and R, and that will give you P of R. All right? So if S is a variable that takes on two values, this is P of S equals 0 and R plus P of S equals 1 and R. And we can use the rules of probability to then tell us how to decode For example, if someone tells us R and we want to know how probable alternative values of S are, that's called the posterior probability of S. You get that by taking the two versions of the product rule over here. The thing we want is on the right-hand side here. So we'll divide through by P of R, and we'll get the answer. So this is P of R given S times P of S divided by P of R. And P of R we can compute using the sum rule, which we just wrote down over there, so I won't write it again. Well, I will actually. Let's write it down. I'll go one extra step. P of R is, we can take each of those terms over there, P of R given S equals 0 times P of S equals 0. We can use the product rule to write each of them out explicitly. Okay. So that's the rules of probability that tell you how to do inference. That tells you how to do decoding. And we can take an example R vector, say 0, 1, 1, and we can apply these rules. So this will tell us not only that this is a sensible decoder, but it'll tell us how probable each of its answers is to be correct. So, for example, if you receive 0, 1, 1, then the two things we need to know over here, we need to know this thing which is called the likelihood of S. And here we've got the prior probability of S. So we need to work out what's the probability that R has that value if S is equal to 0. And we need to know the probability of R if S is equal to 1. So what's the probability of getting 0, 1, 1 out if the sender was trying to send a single 0? Well, there had to be a non-flip, which has a probability 1F, 1 minus F. Then there had to be a flip. Then there had to be another flip. So that's the probability of getting that value of R if S were 0. That's the likelihood of S equals 0. If S were 1, what's the probability of getting 0, 1, 1? Well, in that case, there would have to be one flip in the first bit, and then both of the last two bits would have to be not flipped, and each of those independently has a probability 1 minus F of being not flipped. Okay, so that's 1 minus F, F squared, and this is F to the 1 times 1 minus F. And this exponent here, which in this case is 1, is the number of bits that would have to be flipped for this hypothesis to be right. Number of bits that would have been flipped. Well done, thank you. And this 2, which is no longer missing, is the number of agreements between what the transmitted vector would be for that S and the received vector that we're actually dealing with. Okay, and the more agreements you have, the bigger the likelihood is, because 1 minus F is bigger than F. Okay, so let's now derive this decoder. Let's make an additional assumption. We can only answer this question if we say what the prior probability of S is. Then we can get an answer for the posterior probability. And I'm going to say the following. I'm going to say if the probability that S is 0 is a half, and obviously the probability that S is 1 is a half, then we can actually write down the inference. The probability that S is 1 given R is 0, 1, 1 is 1 minus F squared times F times a half divided by the same term downstairs like this, plus the other term, the other explanation, and now we can simplify this lot. And when you cancel everything out, you get 1 minus F. So we've now answered, in that table we just had, R going to S hat. We've looked at one row of that, the row that says 0, 1, 1. And now what we've worked out is the probability that S is equal to 1, given R is 0, 1, 1, is, in fact, 1 minus F, which is 90%. So it was a sensible thing to say you should guess a 1. All right, and now you can repeat that for all 8 possible answers. Almost all of them will come out just the same sort of way this one did, but if you receive 0, 0, 0 or 1, 1, 1, you'll get a slightly different answer for the probability of what the decoder says you should guess. So, just to finish this off, I'm labouring it because it's good to be clear on a simple case, then we can go and do more complicated ones. The probability that it was a 1 is bigger than the probability that it was a 0, so S hat is 1 is the best guess. Okay. And it's the best guess because it involved the smallest number of flips. Okay. So I'll leave as an exercise doing the case R is 111, so you can work out the posterior probability in that case. So now we have a new task. This was using probabilities to do inference. Now what I want to work out is how well does this decoder perform So this is an example of forward probability. I want to ask the question, if we use a repetition code to encode S, we send T over a binary symmetric channel with a flip probability F, and then we use the majority vote decoder to give us our S hat. What is the probability that S hat will not equal S, where I'm talking here about a single bit? So we send one bit over the channel using this procedure. What's the probability that the S hat we end up spitting out of our decoder will not be the same as the bit that went in? Please have a chat to your neighbour. Okay, any answers? The flip probability is F. What's the probability of an error of this system? Anyone? What probability distribution are you thinking about? Anyone? The binomial distribution, imagine that. Okay, so it's the binomial distribution, and what outcomes would cause this thing to happen? Which outcomes do you need to look up in the data book? Two or more flips in a block. Okay? So the probability of 3 flips in a block is F cubed. That's pretty unlikely for them all to be flipped. The other thing that could happen, and these are exclusive possibilities, is that there's exactly 2 flips, and that's the more likely thing, so we should really focus attention on this term. How probable is it that 2 flips will occur in a block? It's 3 f squared 1 minus f, which you can read out of your data book on the binomial distribution. Okay, there's 3 ways of it happening. That's where the 3 comes from. There's 3 ways of choosing which bits are flipped when you're flipping 2 from 3. Okay, and so that's roughly 3f squared plus some other stuff, so minus 2f cubed. This is the dominant term, the leading behavior. All right, so what have we done so far? We started out with no code. And we had a probability of bit error which was f, for example, 0.1. And when we didn't use a code at all, I'll call that communication at rate 1, because every time you use the channel, you are attempting to send 1 bit. Then we invented the repetition code, which has got a rate of 1/3. So R3 has a rate of 1/3. You send 1 bit for every 3 uses of the channel, and its error probability is roughly 3f squared. So there's some good news. Assuming that f is a small number like 0.1, the repetition code is making things better, but the bad news is the rate has gone down. So remember, what we want to do is we want a system solution that gives us an error probability of about 10 to the minus 15, or maybe even 10 to the minus 18. We could continue with repetition codes. And a homework problem is to work out how many repetitions do you need in order to achieve 10 to the minus 15. Assuming that we're using a repetition code. I'll call this probability of bit error PB for short. Okay, so that's a homework problem, and I'll tell you the answer for free. It's about 61. So, we wanted a system solution, and here is one solution. Let's say that this is a single disk drive. What we do is we package up 61 of them all inside a box, like this. We keep on going, and then we end up with this great big stack, and we put a single wrap around it, and we say this is 1 gigabyte disk drive. It's actually 61 gigabytes of disk drive inside, but we say it's a 1 gigabyte disk drive, and now you copy the file onto all of the disk drives, and you use a majority vote, and out comes your answer. And that majority vote will be right with a probability of 10 to the minus 15 for each bit. So you may have one happy customer, but you probably wouldn't have 1,000 happy customers. And you've got a very big stack of disk drives hidden inside this box. Okay, so that's one option. We can repeat lots of times, and we can get the error probability down. And if your customers say, no, 10 to the minus 15 is not good enough, then you just say, whoops, okay, we've got to add more cost, more disk drives, so you put even more disk drives in the box, and you can still achieve any target, but the cost goes steadily up. Okay, let's now get to the exciting bit. Where can we get to on this diagram? I'm going to tell you another way of making codes, which is to use parity bits, which Goss suggested at the beginning. I'm going to tell you about the 7-4 Hamming code, and then I'm going to tell you Shannon's result for where we can get to on this diagram. So here's how the 7-4 Hamming code works. It's called the 7-4 Hamming code because it takes 4 source bits at a time and encodes them into 7 transmitted bits. So we're going to have 3 extra parity bits, and it works like this. We write S1, S2, S3, and S4 into these circles here, and then we set the remaining 3 bits, which we'll call T5, T6, and T7, such that the parity in each circle is even. So let's do an example. I'm going to encode for you 1, 0, 0, 0. So we send S in the clear, 1, 0, 0, 0, and then we're going to send 3 more bits afterwards. And those bits are determined by writing 1, 0, 0, 0 in order. And then we find the parity in this circle, which is 1, and we put a 1 there, so that the total parity is even. We put a 0 here, and we put a 1 there, and we read them out in the right order, 1, 0, 1. Okay, that's the encoder. Let's do one more example. 1, 1, 1, 0. So 1, 1, 1, 0. Parity in here is 3 so far, which is odd, so put in another 1, and that's now even. And this is even already, so we write 0, and this is even, so we write 0. So that encodes to 1, 1, 1, 0, followed by 1, 0, 0. Okay. Now, that's the encoder, and we need a decoder for ourselves. And just as for the repetition code, the decoder is going to be the decoder that spits out a guess S that differs, whose transmission, it needs to spit out the S, whose transmission, T of S, differs from what we received in as few flips as possible. Okay. So the general idea is P of S given R is P of R given S times P of S over P of R. And this likelihood term here favored S's where we had the fewest flips. So we want a decoder that comes up with the hypothesis that involves the smallest number of flips. And we'll do that by writing what we receive into the same diagram that we created over there. So we're going to write them in the same order: R1, R2, R3, and R4, then R5 up here, R6, and R7. Now, because the noise has come along and could have flipped anything, this R could be any vector at all, and it may not satisfy these rules that we had over here, the rule being that the parity in each circle should be even. And what we're going to do is identify which of those rules are satisfied and which are not satisfied. And then we'll use that to identify which bits we think have been flipped. So anything could happen. Let's imagine that we send this signal here, this transmission, and let's imagine that along the way R2 is received flipped. Okay, so what we receive R is 1, 1, 0, 0, 1, 0, 1. We don't know what happened. That's a little secret that we will remind ourselves with, that actually this one got flipped, but we don't know that. So now we write that into this diagram. So we write in 1, 1, 0, 0, 1, 0, 1. And now we colour these circles in accordance with whether they're happy or not. This circle up here is unhappy, so we'll colour that red. That's a sad circle because it hasn't got the right parity. This circle's unhappy because it's only got 1, 1 in it, and it ought to have an even number. This circle is happy. And that pattern of happiness and sadness we'll call the syndrome of the received signal. And now I'm going to tell you a rule for coming up with a hypothesis of what happened. There are many hypotheses that could account for this syndrome because there's all sorts of flips that could have happened. But the rule is going to be find the bit that is inside all the sad circles and outside all of the happy circles, and then identify that one as the bit that must have been flipped. Well, we're not sure, but that's going to be our guess. So inside all the sad circles and outside the green circles is this guy. So we identify this guy as our guess. We guess this was flipped. And so then we spit out our guess for T is 1, 0, 0, 0, 1, 0, 1, and our guess for S is the first 4 bits of that, which is 1, 0, 0, 0, which is the right answer. So in this case, we have succeeded. Now, if actually what had happened was the noise had come along and flipped 2 bits, then this decoding rule is going to go and find a single bit that it can unflip to account for what's happened. So we're going to end up with 3 bits being messed up. So this decoder is not infallible. It is the case that this encoder and decoder can detect and correct any single flip. So any single flip can be detected and corrected. So that's nice, but if more than one flip occurs, then it turns out, and you can prove this as a homework problem, then your guess for S will not be the original S. So this is another code that has the property that if there's only one flip in a block, it succeeds, just like R3, the repetition code. But if there's two flips or more, then we're in trouble. And this diagram on the screen shows the performance of the 7/4 Hamming code. A homework problem is to work out what its probability of error is. What's the probability of a flip of an error occurring when we use this encoder and decoder? And what you'll find out when you do that homework problem is the probability of a block error is roughly 21f squared. You'll find that out using the binomial distribution. And the probability of bit error is about 9f squared to leading order. Okay, so Shannon asked the question, if we make encoders and decoders, where can we get to on this diagram? We've had a few ideas, repetition codes, and I've shown you one code using parities. The question is, what's the boundary between achievable and unachievable points on this diagram? And before Shannon conceived of asking that question, I think conventional wisdom was that the boundary between achievable and non-achievable points just had to be some sort of line going through the origin. Because Sod's law says if you want a really small error probability, then surely you're going to have a really small rate, just like our enormous stack of disk drives that we're imagining. So conventional wisdom knew that points over here were achievable, but conventional wisdom probably was assuming that the boundary went somewhere here. And Shannon proved an absolutely remarkable result. And this is going to be the heart of this sequence of lectures to prove this result. Shannon proved that you can get the error probability arbitrarily small without the rate having to go to 0. So Shannon proved that the boundary between achievable and non-achievable points is a line that looks like this. Everywhere here is achievable, and excitingly, this line meets the rate axis at a non-zero rate. And because that's an exciting place to talk about, we give it a name, and we'll call it C, the capacity of the channel that we're discussing. For example, the capacity of the binary symmetric channel with a flip probability f is 1 minus the binary entropy function of f, where I will define the binary entropy function for you right now. There it is. So there is the line between achievable and non-achievable points. So what does this mean? Shannon spots us selling a disk drive. A disk drive. Here's a 1 gigabyte disk drive, mate. It's got 61 drives inside the box. And he says, you don't need 61 drives in the box to get an error probability of 10 to the minus 15. You just need 2 disk drives. Because for the case where f is 0.1, the capacity, when you work out this formula, comes out to 0.53, which is bigger than a half. So you only need 2 disk drives in the box, and then there exists an encoding system and a decoding system that can correct as many errors as you like. Whatever error probability you name, there exists an encoding and a decoding system that can achieve that error probability. So 10 to the minus 15, no problem, 2 disk drives. 10 to the minus 18, 2 disk drives. 10 to the minus 60, 2 disk drives. That is Shannon's noisy channel coding theorem. So for any channel, there are encoders and decoders that can achieve reliable communication at any rate up to this quantity called the capacity of the channel. I'm going to wrap up now. I've just got 3 things to say. First, the lecture notes for this lecture are chapter 1 in this book, which is a free online book, also available from all your favorite bookshops. You can get it from Amazon, you can get it from Cambridge University Press, and it's free on the website of this course as a PDF. The lecture notes are chapter 1. For the next lecture, I recommend that you read chapter 2. And the remaining lectures of this course are going to cover information theory. We'll continue discussing the noisy channel coding theorem. But first, we're going to discuss the related task of data compression. How do you make files smaller? Then we'll move on to discussing data modeling, pattern recognition, learning, and memory. And we'll talk about various inference methods, approximate inference methods, and neural networks. The final thing I want to say is, please, before the next lecture, have a think about this puzzle. This is called the weighing problem, the weighing puzzle, and it goes like this. You're given 12 balls, all of which are equal in weight, except for one, and you are told that exactly one of them has got a different weight, and it's either heavier or lighter. You're also given a balance, and the balance is one where you can put any number of balls on one side and the same number on the other side, and then initiate the weighing, and it either comes out like this, or they balance. And the task is to identify the odd ball and whether it's heavier or lighter in as few uses of the balance as possible. So that's going to be the first thing that we discuss in the next lecture. Thank you very much for coming. Thank you for listening.